oriented contact, y is a closed oriented manifold. Lambda is a non-degenerate contact form. Meaning that all the orbits are non-degenerate, there's neither transversely in the appropriate sense. J is a generic Walton's complex structure. On R cross Y, satisfying the usual conditions. And then if let's say you have a collection of great orbits with multiplicity. So to be ECH generators, you need that MI equals 1 when alpha I is hyperbolic. But in defining the theory, sort of technical foundations, you also need to look at these things where MI could be bigger than 1 when alpha I is hyperbolic. So I'll just call it an orbit set. So an orbit set is just a finite collection of embedded grid orbits with positive integer multiplicities. And an orbit set is a generator of the ECH chain complex whenever MI equals 1 for orbits. Then this has a topology class. Which is the sum of the topology classes of great orbits with multiplicities. Let's call it gamma. And let's say I have another orbit set. In the same topology class. Then I define this moduli space of holomorphic curves at alpha beta. So this is the moduli space of holomorphic curves in R cross Y with positive ends and covers of the alpha i's, the total multiplicity Li, and negative ends and covers of the beta j's, the total multiplicity Nj. And then there are two key quantities, so there's the Fred-Holm index. Sorry, so there's C and M and B is somewhere injective. Let's not even say that. Okay, so C is in B, we define the Fred-Holm index. Into C equals minus I to C plus twice the relative first strength mass of the contact length field over C plus some commutator constants. And then the ECH index. So the point of the Fred-Holm index is that this is the expected dimension of the moduli space of holomorphic curves near C. And it will be the actual dimension if J is generic and C is somewhere injective. And the ECH index, this I of C, is the relative first strength class plus the relative self-intersection pair plus some different compensating term. And then the theorem, which was the problem from all the equations and inequalities that I stated last time, is that if C is somewhere injective, then Fred-Holm index is less than or equal to the ECH index minus twice the common singularities of C. So this is the key fact which gets ECH off the ground. So why do we care about that? Also, so definition. So given gamma dimensional imply define the ECH chain complex BCC of y lambda gamma j as follows. So it's generated by process alpha equals alpha I for such that the homology class will be ordered as gamma, and the usual business of I equals 1 when alpha is hyperbolic. You can work over Z if you worry about signs, or you can work over Z by 2. And then the differential is the differential of the generator alpha is the sum over all generators beta of the count. I guess I should introduce one more notation here. All the way down here. So imagine a little bit there. So let's let down K of alpha and beta, the set of C and alpha and beta, such that the index of C is equal, ECH index of C is equal to K. So so now I'm going to count the elements of the set M1 of alpha beta modulo the equivalence relation times beta. So the number of times that beta appears in the differential of alpha is counted for M1 of alpha beta. Then what's the equivalence relation? The equivalence relation is two things. So first of all, we run out on the R action. So because J is, the almost complex structure J assumes to be R invariant, so we can always translate the R coordinate to get the roll curve. So we run out by that. That's the usual thing you do in any kind of contextuology. And then one other thing is it should multiply covered curves appear in here, but I regard them as currents. I don't care about where the grand points are. Okay. So that's the definition of the differential. So the claim which requires the justification is that this is well defined. Second, it's a differential. And third, the CCH. Bonded and ground, right, we call the CCH. With YXC down. Okay, so they're actually defined as CH. I need to explain why the definition makes sense, so that I haven't clearly defined. So the proofs of these claims are sort of easy. Number one is kind of easy. Number two is very difficult, and number three is ridiculous. So number one, modulo a couple of minor things I'll explain to you shortly. Number two is a 200-page paper, prepared papers by myself and Cliff Tops. Number three, we don't yet have a direct proof of it, but it follows from Tops' isomorphism with cyber for homology, which is 500 pages. And I think a direct proof of this actually would be possible, but it would still be in the hundreds of pages.
More than 500 or less than 500?
I don't know. Depends how many details you skip. So why does this definition make sense? Well, so what's the issue in proving that D is well defined? Well, we need to know that these things that we're counting form a discrete set. And then we need to show that that discrete set is finite. So if we have an infinite sequence of these things, we need to find a subsequence converging to something in the set. Well, who knows what a sequence of these things can converge to? So to control that, we have the following proposition. So let's see the any curve at MAB. And I'm not requiring this to use somewhere injective, so it's maybe also cover. So the following hold. So first of all, part 0 says that ECH index of C is greater than or equal to 0 with equality if and only if C is a union. By the way, C is also allowed to be disconnected. Okay, so I C equals 0 if and only if C is a union. Covers the trivial cylinders. The trivial cylinder is a cylinder in 4-part cross gamma, where gamma is a rate orbit. That's part 0 of the proposition. Part 1 says that if I guess I should say if your alpha and beta are just any one that says. Not necessarily ECH generators. Okay, so part 1 says if ISC equals 1, then C is the disjoint union of C0 and C1, where C0 is not equal to 0, so it's a union of covers of trivial cylinders. And C1 is embedded and it has both Fredholm index and BCH index equal to 1. Sorry? Yes, J is generic, so I said that at the beginning. I'll say it again. Yes. Your generic means it satisfies some unspecified genericity conditions which become stronger and stronger from one proposition to the next. Okay. But there's a second part of this, which I probably won't get to using it, but we'll say it anyway. For 2, if I is C equals 2, and alpha and beta are ECH generators, then C can be written as the disjoint union of C0 union C2, where I or C0 equals 0, and C2 is embedded. But if n equals I equals 2. That's the proposition. So basically, when, as a differential, we restrict the ECH index to be small, we get good control over what kind of form of diversity we have, even without any assumptions about it to be somewhere objective. So then, the corollary of this proposition is that the differential is well defined. So what's the proof? Or this is actually just some of the proof. So part 1 says that anything that we're counting the differential is still a embedded in x1 piece plus a trivial piece. And so these form a discrete set. Was there a question?
Is the part on the that C1 is the end,
C1, the non-trivial, in part 1, the non-trivial part will have to be connected, otherwise it's bigger than 1. Although in part 2, it's not true. C2 can be the union of 2 and x1 things. Yeah?
Are you allowed to have a disconnected code with 2 pieces of x1 for which only one has to be based on the one example?
Sorry, say it again?
If you have, when you do the, so in case 2, you can have C2 can be disconnected with 2 pieces of x1. Those things appear when you define the UMAP.
So Carl's getting ahead of us a little bit to the UMAP, which counts, and there's 2 curves going through a base point. And the question was, in part 2, the C2 consists of 2 and x1 pieces. Could a curve like that appear in the definition of the UMAP? The answer is generically no, because generically nothing in x1 goes to your base point. Because in x1 things sweep out a sort of 3-dimensional subset of R cross Y. I'll have to come back to that a little bit later. But anyway, so part 1, it implies that this set M1 and alpha beta, modulo translation and modulo not caring about how trivial cylinders are covered, is discrete. So to prove it's finite, you suppose. So I know I can't explain this the whole thing for this, but I'll give you the basic idea. So given an infinite sequence in this set, we could find a subsequence converging to a broken curve. Where in SFT, what we call this a whole working building. So your sequence of curves, whatever they are, it may sort of stretch out into several pieces. So each of these pieces is a holomorphic curve in R cross Y, and the positive ends of one curve are the same orbits as negative ends of the next one. But this whole thing has to have total ECH index equals 0. So it's a basic property of the ECH index, which is one of the exercises of the notes, that if you take a sequence of curves like this and glue them together, then the ECH index is additive. So, sorry, the total ECH index is 1. But that's the sum of the ECH indices of the pieces. And by part 0, each piece has to have ECH index at least 0. That's really helpful. So there's nothing of negative ECH index. So there's one piece of ECH index 1, and then maybe above and below it, there's some pieces of ECH index 0. Now, one then needs a further argument, which I can't explain right now, to show that actually these index 0 pieces cannot occur. And so you just have one index 1 piece. So if this set were infinite, you could take an infinite sequence of distinct points in it. They would converge to something. But because J is generic, this index 1 thing is cut out transversely. So it's isolated. It's an isolated point in the moduli space. And so that can't happen without a configuration. So that's the basic idea of why this set is finite. Questions so far?
Can you give one sentence on how you rule out the I equals 0? Yeah, long sentence.
So how do I rule out the I equals 0 things? So in the definition of this moduli space, I did not explicitly specify what are the multiplicities of the ends of the holomorphic curves of the ring orbits. So I just said, at alpha I, the total multiplicity of the positive ends is I. So the multiplicities of those ends are some partition of the integer mi. I didn't say which one. However, that partition actually is determined by everything I said, if you figure it out. And because of what that partition is, if you stuck an index 0 branch cover, you actually can't put an index 0 branch cover without it. Or you can't have, so this would also have to have flat elements. But because of what this partition is, any branch cover you put above it will have positive fractal index. That's the data that goes into the argument. Other questions? Okay, so I should explain the proof of this proposition. Again, most of the proof of the proposition. Let's see the curve in alpha beta. Maybe it's disconnected, or the domain is disconnected. I should probably be using the word irreducible instead of so maybe not irreducible, but we can divide it into its irreducible C high covered, and these will be connected. Or irreducible. Flat limiting somewhere injective for CI covered with the multiplicity of TI. So any holomorphic curve can be decomposed in this way. So then the question is, how does the index of C relate to the indices of the CIs? So here's the trick. So we're going to define a new curve, C prime. This is going to be the union over I of the following. So remember I said that if you have any holomorphic curve in R cross Y, you can translate it in the R direction to get a new holomorphic curve because J is R invariant. The C prime is going to be the union over I of Ti translates of Ci. So instead of having a default DI full covering of CI, I'm using CI and then different translates of it. But why do I want to do that? Because now C prime is somewhere injected. I got rid of the multiple covers. And because it's somewhere injective, I can apply the index inequality to it. Let's see. I'll use this thing. Oh, I guess, sorry, that's not true. I have to make a simplifying assumption for that to be true. So what I should have said first before I said this is a simplifying assumption is that if Ci is a trivial cylinder, then Di equals 1. Okay. Otherwise, what I said about C prime is somewhere injected is nonsense. So we can drop the simplifying assumption, but it requires a little more work, which I don't have time to do right now. Well, let's just assume that and see what happens. So now we know that the index of C prime is less than or equal to I of C prime minus 2 delta C prime. That's the index inequality. Now, what is the Fredholm index of C prime? Well, if I have the Fredholm index of any holomorphic curve is the sum of the Fredholm indices of its irreducible components. So this is simply the sum over I of Di times the index of Ci. And what about this? Well, the ECH index, so the problems from the exercises I gave last time, the ECH index depends only on the relative homology class of the holomorphic curve. And C prime is in the same relative homology class as C. And there's the difference between them is the boundary of something. So I of C prime is the same as I of C. And the number of singularities of C prime, well, each component, so much as well, let's just leave it as it is for now. Anyway, so I get this. next embedding curve has to be non-negative because J is generic, so there are no negative index moduli spaces. And the Fredholm index of the somewhere objective curve is 0, only if that curve is R invariant. Otherwise, R acts like moduli space, and so the index has to be at least 1. Okay? So this, now if we set I of C equals 0, then all these Fredholm indices have to be 0, which means everything's a trivial cylinder. And that's exactly what part 0 says. If I of C equals 1, then one of these Fredholm indices can be 1, the rest have to be 0. And that gives you part 1. And the C1 has to be disjoint from C0 because the delta of C prime has to be 0. And then for part 2 of the proposition, it mostly follows, except it's conceivable that you could have an index 1 thing with a covering degrees equal to 2. So you need an extra argument to roll that out. And that actually uses the assumption that there are no multiply covering hyperbolic orbits. I'm not going to need part 2 anyway, but that's sort of the starting point for d squared equals 0. Any questions about that? Yeah?
Because it's the reason was the curve, somehow you make so the analysis you use,
Hold on, stop. You have to start again.
Yes. Okay, so when you have a broken curve, right, with base 2, right, so somehow, and then for the part this index, this I equals 0, right, you make a multiple cover setting those. So the analysis you use, you don't need like a oracles when you do this, all this type, so you can do it more.
So, I didn't understand the entire question. Part of the question was do we need polyfolds?
Yes.
So we don't need anything to define the diffraction. To prove that d squared equals 0, we have the 200 pages hard work. It is quite possible that that could be reformulated in the language of polyfolds. I think you would ultimately sort of have to do the same things, but you would be able to put it into the framework. And for proving that the ECH is independent of J and contact form, I'm not even sure if whether or not polyfolds could solve that problem. I mean, if you sort of assume that polyfolds have somehow made all moduli spaces transverse, then it's not clear if that is sufficient to get what I need. You also need stuff, that this has to be homogate with respect to the ECH index. Anyway, this is a very interesting question that I don't know the answer to. Other questions? All right. So that's the proof that D is well defined to modulo minor issues. The proof that d squared equals 0 is much more difficult, and the source of the difficulty is so when you prove that d squared equals 0, you look at a family of index 2 curves. And you want to say that any infinite sequence of index 2 curves has a subsequence breaking into a pair of index 1 curves, and conversely, a pair of index 1 curves can be looped into an end of the index 2 moduli space. So that's the usual strategy for proving that d squared equals 0. But in our situation, it doesn't quite work that way. So an index 2 sequence can be generated into an I equals 1 curve, and then I equals 0 branch cover of going to attempt to summarize it now. However, I can make another remark about why we do not have multiple covered hyperbolic orbits. So you want to see reason number 3, why there are no multiple covered hyperbolic orbits?
What would be the number 2?
So reason number 1 was so that the Euler characteristic would be invariant. Reason number 2 was to agree with center group theory. And reason number 3 is we couldn't do because otherwise gluing theory doesn't work. So here's what happens. So, as I mentioned, the partitions so determined by the ends of the curve are determined by the theory. So, suppose that I have a degeneration like this, in which a positive hyperbolic orbit appears with positive multiplicity. So, in other words, we're looking at, so say I have ECH generators alpha and beta, and we're looking at the index 2 moduli space between them. This thing can break, but the orbit in the middle, there's nothing to force that to be an ECH generator. Maybe it's not. So maybe we break into something where we have a positive hyperbolic orbit with multiplicity bigger than 1. Now it turns out that when that happens, you always get, the ends of the curves always have multiplicity 1. So when I equals 1 curve can never have an end that had a multiple cover of the hyperbolic orbit. It can only have an end that was uncovered hyperbolic orbit. It could have several of them. So you can have a configuration like this, where you have m negative ends of the upper curve and m positive ends of the lower curve. Now you want to glue this together to go back. Now, when you glue this, you have to choose a bijection between the negative ends of the upper piece and the positive ends of the lower piece. So you say which of these things can you glue to which of these things, and then you can do the usual gluing construction. So there are n factorial ways to glue this. Now, when n is bigger than 1, this is even. So if you're working over Z mod 2, then the number of ends of the moduli space that you can produce by gluing this is 0. So in order for but the number of ends of the index 2 moduli space is supposed to be counted by d squared. Therefore, this must not be counted by d squared. And therefore, we do not allow this to be a generator of the chain complex. What? So the number of ends of the index 2 moduli space is supposed to count d squared. The contribution of this configuration to the number of ends of the index 2 moduli space is 0. Therefore, this should not be counted by d squared. And therefore, that's why we don't want this middle thing to be generated. The same thing happens if you use integer coefficients. So if you use integer coefficients, then some work of Bourgeois and Wolfman implies that the gluings alternate signs, so to speak. So half of the gluings at one side and half at the other side. So the same conclusion holds. And a similar story holds for negative hyperbolic orbits. It's just a tiny bit more complicated, so you can see it in those.
why the similar story is not hold for elliptic orbits?
Why does a similar story not hold for elliptic orbits? Can I give a simple explanation? No. So that's the 200-page paper. So we blew in this branch cover of a triple cylinder. So in the elliptic case, these multiplicities actually are completely distinct from these multiplicities. So you can't glue it directly at all. The only way you can glue things is to insert a branch cover of the triple cylinder between them to mediate between the different end multiplicities. By some very difficult calculation, we calculated the number of ways to glue and found that in the cases we cared about, this number is 1. In fact, in all other cases, it's 1. So it's 1 exactly in the cases that we needed to be 1, not in other cases. It's like a conspiracy or something.
Michael,
Yes?
why the breaking with 3 pieces and index P 0 piece in the middle doesn't appear in contact control?
That's a great question. So
Well,
why?
it does, and they pretend to
What? So the question was, why does this kind of thing not happen in contact homology? So if you've used polyfolds or some other machinery to perturb all moduli spaces to be transverse, then you won't see this. However, before you've done that perturbation, this certainly does happen, and these things actually contribute. So if you sort of have an unperturbed, if you've not done an abstract perturbation, then in a situation like this, actually either this configuration consisting of the I equals 0 thing plus the I equals 1 thing, or this configuration consisting of the I equals 1 thing and the I equals 0 thing, actually needs to make some contribution to the differential in SMT or context homology or whatever. I can show you specific examples of this. So the expectation would be that if you do polyfolds, then one of these or the other gets perturbed into an abstract index 1 object. So in context homology or symplectic field theory, I can give you an example where there are 2 generators of the chain complex. There exists no index 1 curve between them, yet the differential coefficient between them must be non-zero. The differential coefficient is not just counting index 1 things, but it's counting elements of the compactified index 1 moduli space that also exist. Okay, anyway, this is getting kind of technical, so let me get back to the basics. So what have we got here? We've got a chain complex, we've got a homology. What structure does this thing have? So I've associated to Y, C, gamma, this BCH of C gamma. But this is a Z or Z2 module. And it has a gradient. So it has a relative gradient. By the ECH index. So that means that if alpha and beta are two chain complex generators, then I can find, well, I'll call I to alpha beta, which you can think of as the gradient difference between alpha and beta, the gradient of alpha minus the gradient of beta. So this is defined to be I of alpha beta Z. So I don't think I spelled this out last time, but The definition of ECH index doesn't require the input of a whole or a curve. You just need a relative homology class of two chain going between alpha and beta. Okay, so this is any two chain with the boundary z equals alpha minus beta, which is a two chain in Y. So this is a well-defined number modulo something. So this is an element of Z mod D. What is D? So if you change the homology class of this thing, well, here's the formula. So if you replace the C by some Z prime, and this is the pairing of the homology class of Z minus Z prime with C1 of the contact plane field plus twice the point gradient with gamma. So that's the ambiguity in this number. And so it follows that this is well defined with Z mod T, where T is the divisibility of this class C1 of C plus 2 point gradient with gamma in H2 of YZ mod torsion. Which is actually, it's always an even integer. So we have a relative grading. There's actually absolute grading by homotopy classes oriented to plane fields. But I don't try to explain that now. So this is good enough to get started. There's also a symplectic action filtration. So as I mentioned before, you can define the symplectic action of the generator to be the sum over I of Li integral alpha I vector. Or we could write this a little more concisely as the integral over alpha of that. And then if there exists any holomorphic curve going from alpha to beta, then just like in any other version of context homology, the action of alpha is greater than or equal to the action of beta, because if you look at the integral over alpha of lambda minus the integral over beta of lambda, then using Stokes' theorem, this is the integral over C of u lambda, which there's no convergence problem in this integral because everything's convergent to the orbits at the ends. But the conditions on the almost complex structure implied in T lambda is everywhere by negative on a homomorphic curve. So it follows that BCCL of y times gamma. So this is the span of the generators. With action less than L. This is a subcomplex. And this leads to, so if you take the chronology fast on this, you get well denoted ECHL of y and gamma. And this is called the filter ECH. So this is what appeared in the first lecture when I talked about ECH capacities. But now you see the actual definition of it. Now, so the thing is, the usual ECH over here, that's isomorphic to Cyber-Witten or Hagar for homologies, and it's basically a topological variant of the three-manifold. However, this thing depends heavily on the contact form and not just on the contact structure. It is independent of J, but it depends on that. So if you, so it's really, if you, for example, if you multiply lambda by a constant, then you have to multiply L by the same constant to get the same group. So that really measures the size of things, not just the topology. There's also the contact invariant. Let's call this, I don't know, C. This is the homology class of the empty set in ECH of y, c, 0. Okay. So it follows from this little Stokes theorem calculation that the empty set is a cycle of the chain complex. So d of the empty set is 0. But d of the empty set of non-zero, that whatever eventually would have to have negative action, nothing is negative action. So it's a cycle, and you can check that this gives you invariant, which depends on the contact structure. So while the usual ECH is basically a three-manifold invariant, this distinguishes in context structures. For example, it's 0 for over-twisted ones and 1 for strongly fillable ones. And so it's, it also agrees with the Hagar for its other contact invariance. And it's proved by the people who prove its isomorphisms. So that's almost everything that went into the application that I stated at the beginning. And then the last thing that went into the application was coordinate maps. So we can actually do coordinate maps in a much more general setting than this. So the simplest setting is with exact and conjugate coordinates. So here lambda is a one form on x, such that d lambda is symplectic form on x. The lambda restricted to y plus or minus is lambda plus or minus. So as I mentioned in the first lecture, this induces a map from the filtered ECH So how do we define something like this? Well, the usual thing you do is attach cylindrical ends to this that look like symplectizations. Then you would count I equals 0 curves in symplectization and use that count to define a chain map. Now, so why haven't I done that yet, or anybody else? Well, you saw this proposition that I had a few minutes ago to prove that the UCH differential is well defined. That said that there are no negative index curves. But a crucial step in that proposition was where I used R invariance, so the symplectization, to say you can take a polymorphic curve and translate it to get another one. In coercive, there's no translation action available. And the analog of the proposition is false. And negative index things actually matter. They actually make a contribution to the coercive analog. So that's why it's difficult. That's why we use Simon theory to define it. Anyway, to understand this stuff better, it would really help to have a basic example. But I conveniently had only 1 minute left or less. So, but Benici has kindly offered to go over the most basic example in the discussion section.
Are there more than these here?
Yes, so, I mean, if you want direct computations without using the isomorphisms with other fluid theories, the 3 sphere is easy. And that'll be in the discussion section. It's also in we're noted in the blog, so it sort of breaks it down into a series of exercises. So you can, if you want to be super organized, you can try to think of those before the discussion section. So that one is fairly easy. The P-torus with standard contact forms is complicated, but it's done. That's a nice, and that's actually used for computing ECH capacity. So there's more examples that I showed you. David Farris in his thesis computed it for circle bundles over a surface that is pre-quantization spaces. So in that case, the differential is 0, so you can, so the structure is not that complicated. A couple other examples. After that, usually things like this can't be computed directly except in very basic examples. But that's just what I think is.
One comment on that, if you only want to determine whether the contact invariant is 0 or non-zero, that's sometimes much easier. There are cases where that's relatively easy, but not known in either of the other 2 theories.
Great, thank you. I should have mentioned that. So Chris Wendell has ways to, I'm just repeating your questions so we go out and think what these can determine, in many interesting examples, determine whether the UCH contact invariant is 0 or not, even without a immutable thing, which not necessarily be easily done in the other theories. Yeah.
So on the first lecture, it says that basically this is logarithms that's we use Z2 coefficients, but it's possible to use Z coefficients. What's the problem? Is there any simple way to solve it?
You're talking about whether you use Z coefficients in the words. Yes, yes. There's a slight subtlety which is you have to. The short answer is yes, it's fine. The long answer is some little subtleties. In the paper we used it, we didn't need Z coefficients, and so I didn't go into it. But actually, I'm explaining it in this finance paper. It's not. It's basically okay because Tobbs in part 3 of his ECH equals center paper study orientations. His isomorphism works over Z is basically what we mean. Well, anyway, I didn't explicitly say this, I am done with my questions.
Any last questions for Michael? So, is there an analog of this ECH filtration in cyber-Witten theory? And
Is there an element of this axial filtration inside the Witten theory? Well, sort of. So the center Witten homology is formally the Morse homology is functional. Well, in general, functional is not real value. Only some, in those cases where it's real value, it gives it completely analogous filtration. In terms of the term science derived functional set of Witten solutions. And what the meaning of that is and how you can compute it, I don't know. But then what happens is that you do Todd's deformation of the center-Witten equations, and that center-Witten functional, very roughly speaking, turns into this implemented active functional. You can also do something like this in Hager homology by areas of the holographic disks, or rather the areas of the regions of the Hager surface that you're counting. Although, in the same way that this filtration depends on the contact form, which depends exactly on the Hager diagrams. It's not really what exactly we're measuring.
so I guess I meant, is there something that depends on the contact form in the same way?
So the only way I know how to get something that depends on the contact form inside of Witten theory is to do Todd's perturbation of the equations using the contact form in terms of ECH. Maybe center Witten experts would have other ideas.
More questions? All right, let's thank Michael for